Imagine we would like to know the precise instantaneous amplitude of a sinusoid. Just looking at the function, this might not be so easy. We would have to determine the maximum or minimum, and depending on the sinusoidal frequency, this might take some time, during which the amplitude also might have changed. But if we have a complex exponential with samples given by this equation here, x of n is equal to a times e to the power of j omega n, and then we can use some trigonometry and exponential substitution, and we find that this is equivalent of a times cosine of capital omega n plus j a times sine of capital omega n. And in this case we know x of n, but we don't know a, and we like to know a. This is the amplitude, so we can easily determine the amplitude a only knowing one complex valued sample x of n by taking the magnitude of this complex exponential. So here, in this case here, we have a complex exponential. We will derive something until we have the possibility to have the amplitude of a sinusoid. So here's how we take the magnitude of this complex exponential with the real part squared times the imaginary part squared and the square root, and then we replace here. This is given by the real part and this is the imaginary part, and this is our equation. So observe that this computation of a is independent of the time index n, so it can be done at every time instance. So if we not only have the sine or cosine function in itself, but both, we can easily compute the instantaneous amplitude in this way. This means instead of just having the sinusoidal function, we also have the 90 degrees phase shifted version of it to compute the amplitude. The problem is, if we only have one part, the real part, how do we get this 90 degrees phase shifted version?